The Falling Walls Science Breakthrough of the Year in Physical Sciences. Please welcome Jury Chair Ian Walmsley, Imperial College, London.
So it's good to have Darwin precede you on these things. Well, it's great to be here on the anniversary of the falling of the Berlin Wall, an event of really major significance globally, of course. And I want to now turn to the Physical Sciences Breakthrough Prize. And I want you to imagine what it would be like to be able to talk to someone halfway across the world, knowing that you can't be eavesdropped upon without knowing that that has happened. Quantum makes that possible, breaking the wall to communications whose security is guaranteed by nature. Now, I want you to imagine further that you can do this in space, so you really can have global reach in that conversation. And putting quantum communications links on satellites breaks through that wall to enable us to talk across the world in a secure way. And the prize winner for this year, Professor Jian-Wei Pan, led a team that actually has achieved this, breaking through that wall, what, as William Shatner has told us for many years, the final frontier, to get ourselves into a position where quantum really enables new ways of thinking about how we communicate with one another. We'll hear a video from Professor Pan in the moment, who unfortunately couldn't join us today, but his colleague, Professor Dr. Cheng Peng, will be accepting the award. Thank you.
Ladies and gentlemen, thanks to the organizer for allowing me to participate in this grand event via pre-recorded video. Quantum communication offers unconditional security in principle, yet extending its range has been a significant challenge. We have demonstrated global quantum communication through quantum satellite missions. To achieve high-efficient global quantum communication, the construction of a quantum constellation is necessary. Now we have taken the first step by realizing real-time quantum communication using a microsatellite and a mobile ground station. In the future, we will launch more microsatellites and strengthen collaboration with colleagues from all over the world to jointly build a global secure quantum network.
Breaking the wall of practical satellite quantum key distribution. How advanced light technology is revolutionizing secure communication. Cheng Peng, University of Science and Technology of China.
Thank you, everyone. Actually, my English is terrible. But don't worry, my smart glasses are here and will save today. So, security has always been at the heart of the human civilization. For security, people built the castle in Germany. People built the Great Wall in China. But sometimes people broke the wall to gain freedom and security in Berlin. So, long before the internet, human has already cared about keeping information safe. In ancient Greece, Spartans used a wooden stick called a scuttle to hide secret messages. In ancient China, generals used hufu to matching tiger-shaped tokens to confirm that military order were real. Today, information security protects almost everything we do. our money, our communication, our personal data. For example, the RSA encryption system is based on math mode, a math problem that it is easy to do one way, but extremely hard to do reverse. So with this method, two communicating parties can share a computed result to create secret keys and encrypt message and verify identities. This idea is so clever and is so useful that almost every people in the world are using it. So, but there's still a problem. This kind of security is not fair to everyone. Why? Because the reverse solving is very hard, but not impossible. So we can see the RSA being corrected time and time again. So who has the ability to correct this? Of course, is the strongest government, the richest company, or the most talented hacker, not us, not ordinary people. Moreover, in 1990s, scientist Peter Shaw showed that a quantum computer could one day crack RSA. Now, only a few places, like the United States, like Europe, like China, or some big companies like Google or IBM, are able to develop such computers. This makes the digital world even more unfair. Everyone, no matter who they are, rich or poor, strong or weak, should enjoy the same right to information security. So, how can we make this possible? We need an unbreakable encryption system to achieve true digital equality. It is the final goal of the information security for many years, but it has never been achieved. Quantum mechanics gave us a new solution. About 30 more years ago, more than 30 years ago, some scientists proposed a new method called quantum key distribution. Unlike RSA, which generate key by sharing the communication result, QKD shares quantum states, such as a single photon or entangled photon pairs, to generate the unconditional security key. So, quantum mechanics tell us that matter or energy have their smallest unit. For light, that is photon. It cannot be divided further. Quantum mechanics also tell us that a photon can exist in superposition, meaning it can be several states at the same time. Because of this, we cannot simply copy or clone them. So, based on this, quantum key distribution can never be broken, and can never be broken even with the powerful computer or quantum computer. But this is the first QKD experiment. Because of the quantum signal, like photon, is very weak. The first QKD experiment center key just 32 centimeters. So how to extend the QKD to long distance is the most challenging problem. About 20 years ago, Professor Jian-Wei Pan returned to China and focused that challenge issue. I was very lucky to become his PhD student. This is Professor Jian-Wei Pan, and in the middle, this is me. As you can see, my hair is all black at that time. Back then, we were thinking, when the light travels, photons are always lost along the way. So, how to make it possible, how to make it work around the whole world? The answer is outer space. Beyond the Earth's atmosphere, even photons that have traveled millions of light years away from the stars, can still reach us on Earth. So, using the satellite, quantum satellite, we can greatly reduce the loss of photons and make global quantum communication possible. With this dream, we start our more than 20 years research. To reach outer space, the first step is to pass through the atmosphere. It has an effective thickness of about 10 kilometers. Sorry. In 2005, we completed the first quantum entanglement distribution over a distance equal to this thickness. It was the first time that a quantum entanglement was observed over 10 kilograms, a very large scale at that time. Later, we developed the QKD. We developed the QKD with the decoy state method, which ensure the security at long distance. So, with this, this will help us to turn our dream into reality. Next, we began to consider sending or receiving photon between satellite and Earth. It is not only a scientific challenge, but also a space engineering challenge. So we wait a while. So we did a series ground tests in the Qinghai Lake. To ensure the success, we carried a serious ground test at Qinghai Lake in China. We used the 100-kilometer free space link to simulate the high loss between satellite and ground. We also use a moving platform like balloons to simulate the satellite motion. Based on this test, we achieved a quantum entanglement and key distribution over 100 kilometers. Because Qinghai Lake is one of the most beautiful places in China. We set up our equipment on the island in the middle of the lake. The view was amazing. Local people and the llamas, and especially this young llama, often comes to see our experiments. By the end, we become good friends. Based on this effort, in 2016, we launched MISSIUS, the world's first quantum science satellite. With MISSIUS, we first implemented satellite to ground QKD, and the distance extend from the first experiment. Remember, the first experiment 32 centimeters to over 1,000 kilometers. Thank you. Moreover, using the entanglement source in the satellite, we sent entangled photon pairs to 2 ground stations. In this way, the satellite don't know nothing about the key, even if the satellite is controlled by your enemy. Once the entanglement is verified, the security of the QKD can still be ensured. So, we use the fiber-based QKD networks to connect the nearby cities, and we use the satellite to link distant ones, such as Xinjiang, Vienna, and Calgary in Canada. So far, we have realized the dream we had 20 years ago. Quantum communication can be applied everywhere and can provide unbreakable keys to everyone. Following the MISSIUS satellite, many LEO quantum satellite projects have been proposed worldwide. We hope all satellites can work together to form a uniform network. And there are one more thing. When different companies operate their own quantum satellite, we can combine or mix their keys. This makes the network more secure and not depend on one provider. So making the satellite smaller and cheaper will become the key direction of the future for the future. In the past years, we developed the G9-1 microsatellite, reducing the payload weight from 100 kilograms to 10 kilograms. And the ground station, the ground was reduced from over 10 tons to about 100 kilograms. It can generate about 1 million bits of keys per orbit in real time, making QKD more practical for applications. We're also working with the international colleagues through the International Telecommunication Union to promote the standard of the quantum communication, aiming to make it more practical, to help QKD work together with today's communication system and become a key part of global communication networks. Of course, the foundation of QKD actually lies on the long-distance transmission of quantum states. So this technology can help us transfer the time and the frequency. We have achieved over 100 kilometer high precision transfer and now expanding it to satellite. It will promote the groundwork for the next generation definition of the unit of seconds. Thank you. Beyond the human-generated quantum states, quantum signals, we are also studying the natural photons from distant satellite. Welcome. By performing a kilometer-scale optical signal, we observed that star, right here. This is about 600 light years away from us. That is the result. So that's all. Thank you.